Welcome back to the Deep Dive. Today, we are effectively opening up the hood of the electronics lab.
Right.
And I don't mean we're soldering circuits or, building robots just yet. We're looking at the actual tools themselves.
The stuff on the workbench.
The stuff that sits there staring at you, which you probably just take for granted.
Which, surprisingly, most people don't actually understand. We use them, but we don't know them.
Right. And our guide for this session is remarkably specific. We're looking at source material from Dr. Dhananjay Gadre's Electronic Design Workshop.
Yeah, specifically the 8th and 9th sessions of the course.
For his 4th semester ECE students.
It's a great curriculum because he sets a pretty clear mission right at the start. He basically says that most students, and honestly, a lot of working pros, are stuck in what he calls the RMS mindset.
And he wants to graduate everyone to the transient mindset.
Exactly.
Okay, so let's break that down immediately, because I definitely fall into the first category. I know RMS, that's what my multimeter gives me, right?
Right.
I plug it into the wall, it says 120 volts, 230 volts. It's a nice, steady, comforting number.
It is comforting. That number is, well, it's a lie. Or at least it's a summary. A multimeter takes a while to think. It averages things out. But the real world of electronics is what Dr. Gadre calls Shenvanger.
Shenvanger. That's a Sanskrit term, isn't it?
It is. It translates to something like momentary or fleeting.
Like a blink and you miss it kind of thing.
Faster than a blink. We're talking about things that happen in a microsecond. If you have a voltage spike that lasts for a millionth of a second, your multimeter won't even flinch.
It won't see it.
It's too slow. It's like trying to take a photograph of a speeding bullet using, I don't know, a sketchbook and a charcoal pencil. You're just going to get a blur or nothing at all.
So the multimeter is the sketchbook.
And to catch the bullet, you need a high-speed camera. In our world, that camera is the oscilloscope. That is your transient instrument. It's a window into time.
Speaking of windows and screens, Dr. Gadre takes this really interesting detour into the history of display tech.
He does.
He starts talking about the old CRT monitors, the big, heavy vacuum tube ones, and he actually validated something my mother told me for 20 years.
Oh, yeah.
You know the drill. Don't sit too close to the TV. I always thought she meant I'd go blind or get irradiated.
Well, she was right about the distance, but maybe wrong about the danger. Dr. Gadre points out it wasn't really about safety. It was about resolution.
Because of the pixels.
The subpixels even.
Right.
A pixel on those old screens wasn't just one magic dot. It was a cluster of 3 distinct blobs of phosphor red, green, and blue.
Right, RGB.
But they were physically separate. If you sit too close, your eye is actually too good. It resolves them as 3 separate colored blobs. The image just falls apart.
You start seeing the matrix.
You do. You need distance, so your brain can smudge those 3 dots together into a single composite color. It's a great analogy for what these instruments do.
How so?
We're trying to visualize data in a way our brains can actually process.
And that leads to this mental model of axes that he introduces. This actually helped me a lot.
It's a great way to think about it.
Because I usually just turn a machine on and hope it tells me the answer. But he says you have to ask. What am I plotting against what?
It simplifies the entire lab. If you are plotting voltage against time,
That's your oscilloscope.
that's your standard view. You see the wave shape.
But what if I'm working with, say, a computer chip? I've got like 16 pins, and they're all firing zeros and ones. I can't look at 16 squiggly lines.
No, and you don't even care about the precise voltage. Is it 4.9 volts or 5.1? Who cares?
You just want to know, is it high or low?
0 or 1. So you plot logic against time. That's a logic analyzer. It strips away all the analog noise.
Just the data.
Precisely. And then there's the one that always looks like sci-fi to me. Voltage versus frequency.
The spectrum analyzer.
Yeah, that's for when the world gets messy. Real signals aren't perfect sine waves. They're dirty. They have harmonics.
He mentions that experiment with a smartphone app.
Oh, Firefox. It's great.
You just whistle into your phone.
You whistle. And if you think you're whistling a pure tone, the spectrum analyzer will humble you. It shows you the main peak, the note you're hitting, but then it shows all these other little jagged spikes.
The dirt.
The dirt, the harmonics in your voice. A spectrum analyzer breaks the signal apart so you can see all the ingredients.
I love that. Okay, so we have our high-speed cameras.
Yeah.
But before we get to the star of the show, the oscilloscope, we have to go back to the multimeter.
The humble multimeter.
Because listening to this, I felt a bit called out. I treat my multimeter like a glorified battery checker.
I think we all do. But Dr. Gadre makes a point that inside that yellow plastic box, there is a full-blown computer.
A processor, memory.
And a very precise analog to digital converter. And it's making decisions for us. Take the continuity tester, the beep mode.
I use that constantly. Touch the probes. If it beeps, the wire is good. I never thought about how it decides to beep.
It's not magic. It's a programmed threshold. It measures resistance. If it's below a certain number, usually around 30 ohms, the microcontroller says, close enough, and fires the buzzer.
And above that, silence, or OL.
Overload, which just means out of range.
Then there's the diode test. I always assumed this was just another resistance check.
But it's doing something active. It has to. A diode is a one-way street for electricity, right?
Right.
A simple resistance check uses a tiny voltage. It doesn't really test that. So in diode mode, the multimeter actually pumps a small current into the component. It's actively poking it.
And then measuring the reaction.
Exactly. It measures the voltage drop. For a silicon diode, it'll eat up about 0.7 volts. An LED, maybe 1.8.
And if you put the probes on backward.
It should show AL, overload. The one-way street is closed. No current flows. If you get a reading both ways.
My diode is toast.
It's just a wire now, a dead short.
I also like the bit about protection, because I've definitely stuck probes into a wall socket when the meter was set to the wrong mode.
We've all done it.
Why did it explode in my hand?
Clamping diodes. It's a really clever bit of self-defense. Imagine the input of the chip is connected to two trapdoors. One goes to the positive power supply, VCC, and one goes to ground.
Okay, picturing that.
Normally, those doors are shut. But if you shove in a massive voltage spike way higher than the chip can handle, the top trapdoor bursts open. It dumps that excess energy straight into the power rail.
It clamps it.
It clamps the voltage, so the sensitive brain of the meter never sees more than it can handle. It sacrifices the rail to save the brain.
It diverts the flood.
That's the logic.
Okay, let's move to the hardware that connects all this.
Yeah.
We have to talk about the BNC connector. I've twisted these things 1,000 times. Push, twist, lock. But I had no idea I was holding a piece of naval history.
It is wild, isn't it? BNC stands for Bayonet Neil Conselman.
The bayonet part makes sense. It twists and locks like a bayonet on a rifle.
Right. Quick to attach, impossible to pull off by accident. But the reason it exists is, well, it's because of the ocean.
The Navy needed it for
Yeah.
What, radar?
Radar, yeah. Specifically, think about the lessons learned from maritime disasters like the Titanic.
Wait, connect those dots for me. The Titanic sinks, and we get a better cable connector.
Think about what failed on early ships. Radio was the lifeline. If your radio goes down, you can't send an SOS.
And on a ship, you've got salt, spray, moisture.
The ultimate enemy of electronics. Connections would just corrode, turn green, and the signal would die.
So the BNC was designed to be sealed.
Environmentally sealed. When you twist that lock, it's not just mechanical. It's tight. It keeps the air and the salt out. That reliability is why it moved from Navy ships to every lab bench in the world.
That's really cool. So it's a military-grade, waterproof seal for my little 5-volt science project.
It's overkill, maybe, but it's reliable. And that's everything.
But the connector is just the tip of the spear. We have to talk about the probe itself. This was the part of the lecture where my brain started to hurt a little. The 10x probe.
Ah, yes. This is the deep end of the pool. This is where the physics actually bites you.
Okay, so on the side of the scope probe, there's that little gray switch, 1x and 10x.
Yeah.
I always thought 10x was just a safety feature. Like, oh, I have a high voltage, let me cut it by 10 so I don't fry the scope.
And you're not alone. Most people think that. And it does do that, but that's not why we use it. Think about it. In a student lab, you're working with what? 3 volts? 5 volts? You don't need to attenuate 5 volts. The scope can handle that easily. And yet, Dr. Gadre insists you should always use the 10x setting.
Why?
Bandwidth. This is the tricky part. Your expensive oscilloscope, it's not perfect. The input has a tiny bit of capacitance. Think of it as electrical stiffness or a sponge.
Okay.
It's called parasitic capacitance, maybe 15 picofarads. Now, when you connect that to your circuit, that sponge soaks up the fast changes. It resists moving quickly.
So it acts like a drag.
Exactly.
Yeah.
It creates a low-pass filter. It lets the slow, lazy signals through, but it kills the high-frequency stuff. He runs the numbers in the class. You take a 100 megahertz scope, a Ferrari of an instrument, and you use a standard 1x probe. That parasitic capacitance drags your performance down. You might turn your 100 megahertz Ferrari into a 10 megahertz go-kart.
Whoa! So just by having the switch in the wrong spot, I'm losing 90% of my scope speed.
You're losing the sharp edges. If you look at a square wave, which needs high frequencies to make those sharp corners, it won't look square. It'll look rounded, mushy, like a shark fin.
And if I saw that, I'd assume my circuit was broken.
You would. You'd think, my design is bad. But no, your measurement tool is lying to you.
So how does switching to 10x fix this? It adds resistance, right?
It adds a huge resistor, 9 mega ohms series. But here's the magic trick. Inside the probe, parallel to that resistor, is a tunable capacitor.
Okay, so we have a capacitor in the probe and that sponge capacitor in the scope.
And they balance each other out. Imagine a seesaw. On one side, you have the scope's imperfections. On the other, you have the probe's components. If you adjust the capacitor in the probe perfectly, the math just cancels out.
The math cancels out.
Completely. It's an equation. R probe times C scope equals R scope times C probe. When that balances, the filter effect vanishes. It becomes an all-pass filter. The frequency doesn't matter anymore.
And the square wave snaps back.
It becomes a perfect square again.
So that little screw on the side of the probe, the one I've been ignoring my whole life.
That's the trimmer capacitor. You're supposed to adjust that every single time you use a scope.
You're kidding.
You hook it up to the test signal, turn that little screw until the wave looks perfectly square. That's called compensating the probe.
That is humbling. I have never once touched that screw.
Well, now you know. If you don't touch it, you might as well be guessing.
Speaking of guessing, let's talk about the devil button.
Auto scale.
Dr. Gadre goes pretty hard on this. He says using the auto scale button makes you a dumb fool.
Which, I mean, that feels harsh.
It's blunt, for sure.
I press the button, the scope finds the signal, puts it on screen. What's the crime? The crime is handing off responsibility. When you press auto scale, you are telling the computer, I have no idea what is happening. Please guess for me.
But the computer is good at guessing.
Is it? It finds something. But is it what you're looking for? Dr. Gadre's point is that an oscilloscope is a verification tool, not a discovery tool.
Meaning, I should know what I'm looking for before I look for it.
Exactly. If you design the circuit, you know it should be a 1 millisecond pulse. So you should set the scope for 1 millisecond.
Right.
If you use auto scale, it might zoom in on a bit of noise or trigger on the wrong edge. It disconnects you from the reality of your own signal. It encourages you to stop thinking.
And it stops you from learning the most important control on the panel.
The trigger.
This is the thing that stabilizes the wave,
It
right?
does more than stabilize. It captures the shambanger.
The fleeting moment.
Think about it. If you have a signal that only happens once, like a button press or a system crash, auto scale will miss it. It's looking for a steady beat. But the trigger is you telling the scope, wait, don't do anything, just watch this line.
Like setting a trap.
It's like being a sniper. You say, the instant the voltage crosses 2.5 volts, take the picture. That's how you catch a glitch. If you rely on auto scale, you'll never catch the problem.
I like that analogy.
Yeah.
Auto scale is spray and pray. Trigger is the sniper.
That's a good way to put it.
Okay, before we wrap up, we have to mention the fun mode, XY mode.
Voltage versus voltage.
Yeah, usually we look at time on the x-axis. But here we put one voltage on x and another on y. What's the point?
Academically, it's for Lissajous figures. It's a beautiful way to see phase shift. You put a signal into a filter, measure the output, and the shape tells you the timing difference. A circle is 90 degrees. A straight line is 0.
But the source material mentions a less academic use.
Yes. Since the oscilloscope is basically drawing with a beam of electrons, if you control the X and Y voltages fast enough, you can draw pictures. Video games. Exactly. Dr. Gadre mentions that students have programmed microcontrollers to render Arkanoid the Brick Breaker game right on the oscilloscope screen.
That is dedication. It's this incredibly sophisticated, expensive piece of naval-inspired, physics-compensated equipment, and they're playing Brick Breaker on it.
That's the joy of engineering, isn't it? Understanding the tool well enough to make it do something it was never meant to do.
So what's the big takeaway here? We've covered a lot of ground.
I think it comes back to that dumb fool comment. Not the insult, but the lesson.
Yeah.
The tool is only as good as the person using it. You can have a 100 megahertz scope, but if you use a 1x probe, it's a 10 megahertz scope.
You're the bottleneck.
You are. You can have a brilliant multimeter, but if you don't know how the diode test actually works, you're flying blind. Don't trust the black box.
Understand the physics inside the box.
Yeah.
And stop pressing auto scale.
Please stop pressing auto scale.
It does make me think, though, we're talking about auto scale in the lab, but we have auto scale for everything now. You know, AI writes our emails, algorithms pick our music, cars drive themselves.
We are automating the understanding right out of our lives.
Exactly. If pressing auto scale makes you a dumb fool in electronics because you lose touch with the signal, What are we losing touch with in the real world when we let the algorithms do all the thinking for us?
That is a very uncomfortable question.
That's what we do here. A huge thanks to Dr. Dhananjay Gadre for the incredible lecture material from his electronic design workshop.
Definitely check out his work if you want to actually understand what's happening on your workbench.
Thanks for listening. We'll see you in the next deep dive.